All right, so the, I'm going to be working through this as you work through it, and you're B, no, you're A, 5-6. So the kinematics is just a fancy word for motion without really thinking about why things are in motion. So it's the math behind acceleration and velocity and speed and all those kinds of things. And then so we'll do kinematics in one dimension, things moving back and forth across, down a line on a number line. It could be up and down motion, could be left and right motion, and then we'll add in another dimension and we'll have things that are like moving this way and falling at the same time, and then you get projectile motion, something, a car driving off a cliff or a bullet being shot up in the air that's going like that. But right now we're just doing up and down, left and right. So two important terms. Honestly, they're not super duper important, but they're kind of important. Or scalar and vector, you may have learned these already. Scalar just means has a magnitude or strength. Like a good example of a scalar is mass. Mass is the amount of stuff and the amount of inertia in this. You could think of mass and weight as being the same. And I don't know, this isn't a kilogram, but if it were a kilogram, it would make no sense to say it's a kilogram to the left or to the right or down or up. There's no direction to mass. So that's a scalar. Vectors have magnitude and direction. So this mouse is moving along like this. Not only is it moving with a certain speed, but it's moving to a right. So to really represent this as a velocity vector, we'd have to say it's half a meter per second rightward, or half a meter per second leftward. And half of the vector is the magnitude, which is how fast or how strong. Like when it's forces, I can push down with a...
Which glasses on?
All right.
This one now.
Come on in. Put your phone in the caddy. If I push down here, I can push with a certain force down or up or whatever. Right. Delta, I'm sure most of you are familiar with delta, probably everybody. We don't go over the formula much. Delta is just change in something, and the formula is the final condition minus the initial, which I'll come back to. Here it says if x changes from 3 meters to 1 meter, then basically it lost 2 meters, so the change is -2. These are some of the variables we'll be dealing with, and these are the symbols for them, and it's kind of confusing, and you just need to know that in physics you have to be flexible sometimes, because we'll say speed and we mean something really specific, and we don't mean velocity. We definitely don't mean velocity, but we use v for both of them because s is already seconds. And displacement, a lot of times you'll see a displacement graph, and it has a d in it, which is really for distance and distance traveled. And if you ever are confused about what a symbol means, you can just ask. It's a lot of things get used in multiple ways, and it can be confusing. So, position. We use X or Y in this unit. Just think of number lines, or think of a grid. We've got the Y-axis, we've got the X-axis. We'll talk about something's position along either the X-axis or along the Y-axis. And it's an indicator of distance from the point of origin. So vector or scalar, what do you think that is? It's a scalar, and in the past I would get tripped up by this, but the important thing is it doesn't have any direction of movement implied. So if I say my position is positive 3 meters, I've got a positive there, which kind of tells direction, but there's no movement to it, so it's a scalar. Units are meters. Displacement, this is delta x or delta y. So what do you think that is, vector or scalar? Vector, because it's going to be telling us how much something moved to the right or to the left, up or down, and that sign is going to indicate it. So that's vector. Distance, how far something has traveled from its original position disregarding direction. Distance is not negative. What's that? Scalar. Now this is kind of weird. Distance traveled, or total distance, is just the sum of all the distances. So if I drive to Montpelier, that's I don't even know how far, 45 miles. to the east, and then I drive back from Montpelier 45 miles to the west, my distance travel would be what? Be 90. What about my displacement? Zero. Because I'd end and start in the same place. So overall, my position wouldn't have changed over the whole thing. So it gets kind of tricky. So this is a scalar too. Time, I don't even, if we had more than a split block, we could talk about what time is, but I don't think we'd ever come up with a good answer. And there, if you want to see arguments, just Google, is time a vector or a scalar? And you can, right. And it can only move one direction. It only moves one direction. So I think time, as we do it in problems, if you want to be a nitpicker, time's a scalar, but delta t, change in time, which is always positive, that I guess you could say that's a vector, but direction of movement, usually all this vector or scalar thing is based on motion. So I don't know about time. It just doesn't really matter. I put it in there though because we're going to use it a lot, and it's t. And the units are seconds that we'll use. Speed, so it's how fast something's moving, a ratio of distance traveled to travel time elapsed. What do you think, scalar or vector? Scalar. So you could be going fast in any direction, and it's like the speedometer on your car. It doesn't tell you whether you're going north or south, or it just tells you how fast. Velocity is a vector. Velocity, you have to tell the speed and direction to get velocity. All right, that's that stuff. These kinematics formulas at the top, we'll get to those in a few days, derive some of them, and I'll show you how to derive some others maybe. Now, this is the part that there's a danger it's going to seem too simple and you're going to think this is too easy. What is the point of this class? But I'm just trying to keep it really simple, and I'm saying things in maybe an odd way that physics teachers wouldn't ordinarily, because when we get to the definition of acceleration next, I think it helps people to see the parallel between velocity and acceleration. So velocity of 3 meters per second. What does that mean? If I want to walk with the velocity of 3 meters per second, what do I do?
You're going through 3 meters.
Right, so every second, which is 1 Mississippi, like 1 Mississippi, 2 Mississippi, 3 Mississippi, I need to go about 3 of these floor tiles, because that's a meter. So this would be 1 meter per second, and then meters per second, and then so what was that question? If I have a velocity of 3 meters per second, I'm just going to keep this one. So you can write whatever you want or nothing here. That's how these notes work. We could say that every second I'm going to say, for each second, I add 3 meters to my position. So we're going to get into problems where it'll be important to note that that's not negative 3 meters per second. And if we're talking about somebody, this person who's walking across the floor here or running across the floor, that if they're here, 1 second later, they're going to be there. And basically, they're adding position. So one definition of velocity could be the amount of position that's added every second. And I only say it this way because velocity is your change in position, or added or subtracted. Velocity is your change in position. When we get to acceleration, it's going to be just like that, except it's change of what? It's change of velocity. So the amount of position that is added or subtracted each second. Or you could say more generally, during each unit of time. I have this number line farther down the page, and you're somewhere on the number line. If a second later you've gone from here over to there, then you could say, well, that's the amount of velocity, or that's the amount of position that was subtracted during the second, so you'd have a negative velocity. The average velocity formula, I'm going to write it as v with a line over it, but I won't always do that. Sometimes I'll just write v, sometimes v with a line over it. What are the units for velocity? I think I skipped those on the other page, the ones that we'll be using. Meters per second. We use miles per hour, but it's meters per second. So it's basically just the meters that get added on. That's your change of position, divided by the time interval, or the seconds over which you change those. So velocity is delta x, or displacement, over delta t.
Will will VOs only have a straight line, or will it have an arrow sometimes? Because like the line over V could also have an arrow.
Yeah, to represent it's a lot of times that arrow is just to represent that is a vector, but the straight line represents that it's average. That's just the symbol for that. But a lot of times people would just write either v equals d over t, or v equals delta x over t. Delta t gets left out a lot. It's the time interval. 19. All right. So average velocity, I already put the symbol up there. It's v with the line over it, but not always. When we measure velocity, average velocity is what we'll actually measure. You can't measure instantaneous velocity. If somebody gives you a graph like the graphs we were making yesterday, and maybe they tell you the equation for this curve, you can use the equation to figure out the exact velocity at any given moment. But if you're watching somebody who's walking along, you can't get their velocity at one little infinitely small moment in time, because in order to do velocity, you have to watch them and see how long it takes them to go from here to some next little spot. So it's velocities that are measured are always average velocity. Instantaneous velocity, there's such a thing. We'll say, what is the velocity at this point in time, and you can kind of infer it, but you can't really measure it. Initial velocity, the symbol is v0. Now that's the one we use the most, but later on we'll be using maybe vi for initial velocity. Just be flexible with symbols. Final velocity symbol is just v. So sometimes we'll write VF to be really clear, and sometimes we might even use primes and things when we're doing coefficients of restitution. But for now, 0 just means at the beginning, and you leave off the 0, that means final. So a little bit of practice. An object leaves its initial position and travels to a new position. What are the object's initial position, final position, displacement, blah, blah, blah. So looking at this number line over here, here's x, here's x0, here's t equals 7 seconds, here's t0 equals 5 seconds. What's the initial position? You can just blurt it out. You don't have 6 meters. Yeah, x0 is right there. So that's the initial position, 6 meters. And if you really want to emphasize it's positive 6, not negative 6, you could write positive 6, but that'll just be assumed unless you have a negative there. Final position is what? Negative 2. Negative 2 meters. And displacement, or change in position. Negative 8 meters. So you can either look at this and just say, here's where it was in the beginning, here's where it is now, how much did the position change, and did it change in a positive or negative direction, or you can use the formula, which I'll just write delta x, you don't have to, equals final position minus initial position. So it's negative 2 meters minus 6 meters, which is negative 8 meters. But really, you don't need to go through all those steps to do that. Most of you, I wouldn't think. Final distance from the origin, distance from the 0 mark. Is it 2 or negative 2? 2, because distance is always positive. Average velocity. So I'll just write the formula and we'll check. So average velocity formula is the change in position, or the displacement, over the change in time. And the displacement was -8 meters. So that's which way it went and how far. And then the time, do I use 5 or 7 or something else? Yeah, change in time. So I could do final time minus initial time, but you could tell it's been 2 seconds. So -8 over 2 is -4 meters per second as the average velocity. All right. I'm realizing a weakness here. I don't have an average speed formula. So let's. What do you think the average speed is? 4 meters per second. So velocity is displacement over time. Speed is distance over time. Oh, sorry about that. So instead of -8, it's just going to be 8 meters in 2 seconds. So 4 meters per second. Most of the time, speed is just going to be the negative or the absolute value of velocity. Are you here for the second split plot?
Am I here? I don't know. Is it 922?
922. Yeah. So come back in a little while. All right. If you have questions, jump in. But this should be pretty easy stuff. Supposed to be. Supposed to maybe even feel too easy and annoyingly easy, like a waste of time. But it's not. So this page, I'm going to go through this. Your assignment for homework is to do the next page, which is pretty much the same thing, but we'll do this one together. So there was this object that you could imagine this is moving in front of a motion detector, just like the ones you walked in front of. Here it's starting out right at the motion detector and then moving away with what? Is this changing speed or constant speed? Constant speed. And then all of a sudden it's got constant faster speed in the other direction. Is it possible to actually have a point like this? What would you have to do if you were walking in front of a motion detector and you were doing this and then suddenly you wanted to do that? What happens here? Change of direction, and you have to go from fast moving away to fast moving toward instantly, which you can't do. So all these points, they can't. What's that?
If you handed the cardboard off.
Yeah. So you could have somebody walking away, and then you hand it off to somebody who's walking toward, and then you hand it off to somebody who's walking away. Yeah, that'd be pretty cool. Anyway, this is like what we were doing yesterday. But this is just asking about segment A. So what's the displacement for segment A? Starts here, ends there. 8 meters. So you're going from 0 to 8, we're gaining 8. How about the time interval? 4 seconds. So here's the starting time, there's the ending time, 4 seconds. So what's the average velocity during A? 2 meters per second. And you don't need to write it up, but I'm going to write it. 8 meters over 4 seconds. 2 meters per second. I'm just trying to leave a good trail for anybody who's following me. The distance traveled, 8 meters, which happens to be the same as the displacement in this case. And the position at the end of the segment, 8 meters. Okay, so now B. What's the displacement for B? Not 8. -8, because it's going from 8 down to 0, so the change is -8 meters. And the time interval, delta T? Yeah, so the interval starts at 4 seconds, ends at 6, so it's 2 seconds. So the average velocity is?
-4.
Yeah, -8 over 2, so it's -4 meters per second. So just mathematically, what is this velocity? And this velocity, what are they on the graph? They're the slope. So velocity is the slope of a position versus time graph. And guess what? When we get to a velocity versus time graph, guess what the slope is there? If you take the slope of position versus time, you find out how much your position changes with every second. That gives you velocity. If you make this velocity and you find out how much your velocity changes every second. Acceleration. It'll be acceleration. So then when we get to those, like the slope of one is the next one, and then the slope of that one is the next graph. The distance traveled in B would be 8. And position at the end, 0. All right, now the entire thing. So this is asking about the entire trip, all the way from here to there. What would the displacement be for this entire trip? 4 meters, because the start is at 0, the end is at 4, and it doesn't matter about all the back and forth stuff. And the time, delta t, 10 seconds. So the velocity is 4 tenths, 4 over 10, 0.4 meters per second on average. The distance traveled, I can't remember, I haven't done this in a while. 32, yeah. So this is 8 meters, another 8 meters. So that's 16, plus another 10, that's 26, plus 6, which would be 32. And the position at the end?
4.
That's all really easy stuff. The last thing is to take this position versus time graph and make a velocity versus time graph. And part of this we've already done. So we have the first interval from 0 to 4 seconds. What was the average velocity for interval A? It was 2 meters per second. So on this graph down here, the average velocity is just constant from 0 to 4 seconds. And what's the average velocity for interval B? -4. So we calculated it here. This was -4. And we haven't calculated C. So what's the velocity there? Do some mental math.
5.
What's that? 5. So we're just looking for the slope of this. And the slope is the change in position, which it goes, so the displacement is going to be 10. And the time is 2. 10 over 2 is 5. So the velocity for that interval is 5. And you can see here, this is we're getting an impossible graph. You can't just jump from 2 meters per second in a positive direction to -4. If you want to connect these, you can. I mean, this can't really happen anyway. But on the velocity for this last one, I'll write it out. I'll do the average velocity is the displacement, which is going from 10 to 4, so that's -6. And divided by the time, which is going from 8 to 10, which is 2, so -3. That's it. So your homework, which you could probably do in the next 4 minutes. I don't mind if you get your phones out now, that's fine. We end here at 9:19, that's all we have time for. Homework is just to do this next page, page 4.